Hello, welcome back to another video on Science 10. Today we'll continue to take a look at global energy transfers through our biosphere. Previously, we have looked at the concept of how our biosphere is made up, and specifically how some basic aspects of how climate influences our everyday lives as well as organisms on this planet. So, put simply, a climate occurs in every aspect of our biosphere and influences every aspect of our lives on this planet. Okay, and the next we're going to take a look before we jump into taking a look at some data and analysis and climate change. We want to take a look of how climate happens, to for the lack of better choice of words, or to be more a little bit more technical, is what are some factors and influences to our climate. Specifically, how is energy being transferred? That's the topic of our unit, right? How is energy transferred through our biosphere? And today we're going to take a look, only going to take a look at the start of all this, the source of all energy. And you can see here, all energy required, at least for the purpose of our study, okay? Not from the Big Bang, even though technically it is, but we're not going that far back, come from the sun, okay? So whatever powers the Earth, the same energy that powers Superman. It is correct, some energy does come from the Earth itself, but we're not going to be spending time too much on geothermal energy. Our focus is solar energy or radiation energy. Solar radiation energy. We're going to use solar energy because it's way easier. It's one less word. But if you say solar radiation energy or solar radiation, they're talking about the same thing. And I cannot spell. Spelling is apparently not my thing. Oops. Spoilers. I keep picking the highlighter. As you can read, solar radiation is not just the yellow light that we see, or technically it's a white light. Okay, light C, because that's only the visible light. Energy is actually the radiation energy, the radiant energy is actually transmitted via something called electromagnetic waves, or electromagnetic waves, which we will look into in Physics 30. Okay, but in general, there are basically various photons, or quote unquote lights, at different energy levels, from high energy, such as ultraviolet, right? Ultraviolet, or gamma radiations, right? These are really high frequency and high energy ones, to low frequency ones, to things like radio waves, which you listen to, okay, which we use to transmit, like CBC News, or even our TV signals. Okay, because they have lower frequency, but they have longer wavelength. Those will be discussed more in physics, okay, in Physics 20 and 30. But just remember, they are traveled by electromagnetic waves. Okay, so they're basically light, so they all travel at the speed of light, and those energy from the sun to here, okay, traveling at the speed of light, just reminding you, okay, eventually reaches us. Okay, some of the energy, of course, is converted to chemical energy through photosynthesis. We know that, remember, okay, but vast majority of it, okay, vast majority is actually converted into thermal energy within our biosphere, not just atmosphere, okay, our biosphere as a whole. So a region's climate is determined by the amount of solar radiation, basically how much thermal energy we get, right? How much thermal. But remember from physics, the second law of thermodynamics, is energy conversion 100% efficient? Do all of energy convert to thermal? Okay, think about that. We'll talk about that a little bit later. Okay, we know some of them become photosynthesis and some of it becomes thermal, but is all of them being used? Affect 100%? Okay, think about that. But anyhow, the climate is primarily determined by the amount of solar radiation striking in that region, and it's not the same. If you look at a ball, if a ball is rotating perfectly perpendicular to the solar radiation, okay, if it rotates, if in the picture here, if it rotates this way, then every part of Earth should get approximately the same amount of radiation all year long. But that's not true. As you see, that's because, okay, I'm going to erase it because that's not what actually happens. That's because our Earth is tilted at an angle of inclination, okay, about 23.5 degrees. Okay, it's rotating. Now, 23.5 might not seem very big, but think about how big the Earth is. So it's actually fairly significant for a planet the size of the Earth. All right. Now, the insolation is not equal for different part of the planet. For instance, for the amount hitting the equator versus the amount hitting the poles, for instance. Okay, and well, you will discover an activity is not the same over the seasons as well. So because of the angle of incidence of the angle of incidence of solar rays, which is the angle which so the sunlight coming in is the sun, solar radiation, right, carrying those solar energy, right? When it come in like that, it's gonna make an angle. We can make an angle with the surface of the Earth, as well as perpendicular. This angle we call the angle of incidence. Not the angle with the ground. Not the angle with the ground. I'm not. That we'll talk. This will once again be studied more in Physics 20. Okay. It's the angle it makes with perpendicular. Because of the angle of incidence, remember that's tilt of the Earth. Because tilt of the Earth, the angle of incidence is different depending on where which region it is. Right, the angle of incidence is different from there, as you can see in the picture. The angle of incidence is like that. Well, and this one is 0, right? 0. So angle of incidence is different. Okay, so that actually caused what I'm trying to say is sorry, I got paused here for a second because when I typed up it's a little wordy. And the angle of indentation, the climates with the highest temperature, okay, and little variations near the equator. While during the poles, there are much more variations near the poles. Okay, so summer and winter, the variation in temperature, and the daylight hours is changed a lot, and of course that have an impact on their climate. Okay, and don't forget, not only is the Earth rotating, which causes temperature variations and hours of daylight, things like that. That's Earth's own rotation. The Earth itself is in orbit around the sun for about 365 days. If you include leap years, it's a little bit more, 365.5. So it's tilted while it's rotating, right? It's tilted. So that means at different points during the year, different part of the Earth is going to tilt towards the sun. The northern hemisphere tilt towards the sun between around this time. Okay, tilt towards most around that time. That's summer solstice for us. But at the same time, the southern hemisphere tilt away, right? Away from the sun at the same time, right? The opposite is true for southern. So they have their winter solstice while we have our summer solstice, and vice versa. Okay, vice versa. So think about how that may change, how that may impact our climate throughout the year. Okay, remember we have the same June and we have the same December, right? We have the same June, we have the same December, but what happens when we're summer here? What happens when it's in the southern hemisphere? So you have a solstices, and of course, then you have September and March, where the number of daylight is approximately equal because our Earth is tilting this way, but our sunlight is shining into the page. So imagine you are the sun, and you're shining the light, so it's shining the north and south hemisphere equally. Okay, equally. So those are called equinox, equal. Okay, those are called equinox. So here's a picture describing Earth's seasons. Of course, this is December, so winter. This is the a summer solstice and the northern half, right? The north is tilted. Remember, the Earth is like that. Okay, tilted. Okay, so the north half is tilted towards the sun. Okay, so this is a summer. When it's September halfway, remember the Earth is like that. So about equal amount north and south. Okay, number 3, when you go all the way around, once again, Earth is like that, but the south is more tilted now, right? South is more tilted. North is more tilted away. I think I made a mistake. Let me fix that. Keep picking the highlighter. Okay, the Earth is like that. So now because the sun is shining about equally this way, but now if it's shining, you notice the southern half is facing the sun, so it's south summer, north winter, and of course then it goes back around again. Okay, it goes back around again. I did make a mistake here because I drew on the wrong picture. All right, it's this one here. So the equator is here, right? The equator, so the north half and south half. Even though I know it's the dark side, haha. Okay, but the north side and south side is getting equal amount of sun because they are, the tilt is not towards or away from the sun. The tilt is parallel, perpendicular to sun's rays. Anyway, okay, now why does it tilt, change the season like that? Why is summer warm? Why is winter cold? I guess we could say. Okay, why is it like that? Why is it like that? Well, that will come in the activities you're about to try a little bit later. Now, of course, remember what I said is 100% of the sun rays being absorbed and become solar energy, becomes thermal energy that we could use in our biosphere. The answer is no. There is absorption for sure, and when it's released later, it's also not 100% effective. So we'll take a look at that in a bit. So the incoming rays first. So the sun coming from the sun at speed of light, reaching the Earth. Okay, immediately some of the particles in our atmosphere reflect it. Okay, the direction of the ray changes and go right back into space. Okay, go right back into space. But some are absorbed. A majority of it are absorbed. Okay, converted to a different form. Okay, which we can actually later use. This occurs in all 3 components of biosphere. Okay, so absorbed energy is re-emitted as heat. Okay, which drives the hydrological cycles. Okay, through something called convection, which we'll take a look at later, through our air and water, and of course used for photosynthesis. So that's absorbed. Reflected goes right back to space. It doesn't do anything. Okay, that's always going to be some reflected. And by second law of thermodynamics, right, we know some of the energy is going to be, in this case, our output is thermal, but the reflected rays are you can think of as our wasted energy that goes right back to space, or it's they're absorbed elsewhere, maybe. Okay, so reflected energy doesn't get absorbed right away, basically. And in terms of absorption, there are various levels of absorption here. Oxygen and nitrogen absorbs really high energy radiations as gamma rays and X-rays to protect us. Once they absorb, they usually release it back into space. So release it back into space. Ozone absorbs UV in the stratosphere. Carbon dioxide is a water vapor, absorbs infrared. This is infrared radiation, also known as heat. This is the heat we feel. It's mostly infrared radiation, but visible light and radio waves are mostly not absorbed, so that's why we can see the light. Okay, we can see the white light coming from the sun. Okay, so most of the radiations, radio waves, of course, are not received, so that's why we can actually observe it, because of their long wavelengths and actually not absorbed. As to why they're not absorbed, yeah, actually, it is a very interesting topic which you will study in Physics 30. Why are not visible light radio waves absorbed? They still interact, but they're not absorbed because something called photoelectric effect, actually. Anyhow, and of course, there's also the cloud cover atmospheric dust that reflects light as well. So those are not air; those are actually water and solid particles floating in the atmosphere. They're part of the atmosphere, but they're not gases. Okay, they happen in the troposphere, and it varies by region. And we have been adding more to it. They reflect radiation back to space immediately. Okay, and they also absorb the energy emitted by Earth. So if you can think of this, you can think of the ground, and you think cloud here, solar radiation get bounced off, but Earth's radiation also get trapped, right? Also get trapped. So the Earth stays warm, while some of the harmful radiation got bounced off. Okay, we're not talking about the pros and cons of this. It's just how it happens. Okay, and of course, I just mentioned dust are the same thing. Volcanic eruptions create lots of these. Okay, volcanic eruptions, if a volcano explodes, doing lots of cloud. And then, of course, it's going to create significant climate change, right? Much more significant climate change than the regular cloud and dust levels we have. Okay, trapping more heat on Earth, and of course, reflecting more rays from the sun as well. Of course, we also have to have a way to measure. We are not going to do any math with it, but the terminology to talk about the percentage reflected is called albedo. Okay, so higher albedo, higher percentage reflected, right? That's percentage reflected. This is more reflective. Okay, higher albedo, low albedo, which means less reflected, more absorbed. Color, in fact, reflectiveness. Before you read any further, which color do you think has a higher albedo? Light or dark? Okay, light or dark. But anyhow, the shininess and the color, of course, impacts the albedo. So you can see, the examples here. This is ice sheet. This is cloud and dust. Well, it's mostly dust because from volcano. Right, the cloud is over here. Cloud and dust and ice have higher albedo than forest, soil, and the ocean, which you can see is darker. This one have lower albedo. Right, different colors, so it stands out. So the lower albedo, low albedo. All right, so that's how that's the terminology. If here scientists talk about albedo, that's what we're talking about, the reflectiveness of a planet, of a surface. Finally, absorption of thermal energy energy is also absorbed in an atmosphere primarily by our greenhouse gases, specifically when it's leaving. Remember, cloud is one example, but they're not really. They are still gases. They are still part of our atmosphere, but they're not gases. But in general, okay, remember, solar ray comes in at some point, right? The solar radiation comes to the ground. The ground absorbs it and releases some of it back into the planet, back into the surface, and back into space. But if there's some greenhouse gases here, or greenhouse particles there, some of the heat's going to leave, some is going to leave, but some of it's going to be left behind. So the heat is trapped, right? Heat is trapped. Remember, reflection doesn't go one way, okay? Especially for something like greenhouse gases and clouds, right? It doesn't go one way. Radiation from Earth, reflected radiation from Earth to space is also trapped, right? It goes both ways. So if heat is trapped, that may increase the temperature, okay? Increase the temperature of a certain region, okay? Keeping the planet warm. It is a good thing because it keep it with some reasonable temperature kept here. That temperature will support life. Okay, that temperature will support life. Otherwise, if all the radiation come to Earth and we release all of them back into space without actually some of it being trapped to drive convection, once again, something we'll talk about, there's no energy transfer in our biosphere, life won't happen. So as I mentioned down here, without greenhouse effect, Earth would be 33 degrees Celsius cooler. That's not very cold. That's not very nice for us to live on, okay? And because the Earth will be completely covered in ice, and I do not think life will be as the way we know it, okay, as we know it. But too much of it also have problem because that leads to, of course, too warm, the opposite of being too cold. So all in all, in summary, for whatever we said, all the energy came from the sun. This is the source, Superman symbol. Okay, it's a source of our energy. Okay, all the energy came from the sun. It's from solar radiation. When it comes in, majority of it gets absorbed by our surface. Okay, by the surface into our biosphere. Okay, some of it is reflected right away. Some was reflected right away. The Earth, once it's absorbed, will release vast majority of it back into space. Okay, back into space. But on its way, greenhouse gases will trap some heat back inside. Of course, once released, those trapped heat will dry. The heat that's being released by the surface will drive the convection, the heat transfer through our biosphere as well. Okay, and of course, the reflected ones keep the Earth warm and keep the energy transfer going. Okay, keep the energy transfer going. But once again, if you have too much, there may be a problem. And just like everything, when you have too much of anything, it's not good. So this picture summarizes the entire process of how the sun provides our biosphere with solar energy. Okay, so visible light and UV reflected in the form of UV light, and of course, some of the energy is trapped where greenhouse gases. Now we studied how solar energy is used. There is another measurement that you probably hear is how to calculate effectiveness, I guess, of or the usefulness of solar radiation, and of course that's called the net radiation budget. And radiation budget, basically, it's incoming light subtract outgoing light. Okay, so how much radiation come in towards Earth, subtract how much is leaving Earth. So that is the net radiation budget. And so that's the terminology you will hear. Just once again, introduce that terminology to you. And on average, all energy absorbed by the biosphere is emitted back into space. But if the balance is changed, as we have less and less get emitted back to space and being trapped by our greenhouse effect, so the incoming basically is greater than outgoing, right? The budget is going to become positive, right? Net budget is become positive. So this one, the net radiation budget, okay, it's bigger than zero, your tends to warm up if it stays up. If outgoing is less than incoming, right? When at zero, what am I doing? Net radiation budget, if it's less than zero, right? You're not absorbing enough light, but we're releasing a lot of heat, okay, into space. Now, that's not quite gonna happen according to first law of thermodynamics. This really happens if you count into Earth's inherent heat from geothermal energy, right? Those energies also get re-emitted into space. So we're losing energy, right? So net radiation budget is losing, so we're actually losing energy in the long run. And of course, there's some Well, there's another thing that impacts the net radiation budget. Of course, is also the latitude. Besides the obvious cloud cover and albedo, there's also the latitude. Okay, poles usually have a deficit. Okay, overall, remember, overall it's relatively balanced, but on higher latitude like poles, there is a deficit. Okay, without talking about geothermal energy, there is going to be a little bit of deficit. You're releasing more energy than you're getting in. Technically, you're releasing the same amount of energy, equal amount throughout the globe, but poles are getting less. Remember from earlier, poles are getting less sunlight. Okay, but equator is getting more, so have a surplus. So overall, the planet stays the same. So there is going to be a balance. That some places are going to have surplus, some places are going to have a deficit, like the example we've seen. Okay, and of course, radiations can be transferred from one region to another. So the equator is really hot, the pole's really cold. Some of those heat is going to be transferred from the equator to the North Poles and South Poles. How does that happen? We'll take a look at that next time. Okay, take a look at that next time. Okay, and this is how solar energy comes to Earth and how it's sort of being used. Well, not exactly how it's being used up, but how the energy comes to Earth, reflected, and how it's being trapped, and we're allowed to use it. There is going to be an activity which I'll post on Google Classroom and below in the links, which you can take a look, which discusses why the tilt of the Earth have such a big impact on our climate and on the net radiation budget. And with that, we'll talk about convection and energy transfer next time. And thank you for watching. This one's a little bit lengthy because I think I rambled a little bit. So I'll stop. Have a great day.